start today's lecture 26. I was working on your solution key for the completion problem from chapter 14 yesterday morning. And as I was working through it, things were going fine, but it felt very, very disjointed in terms of trying to see relationships between the examples. And so what happened because of that was I decided I wanted to do things a little differently here for the next 4 days. Today, Wednesday, Friday, next Monday, next Wednesday. In that I wanted to do chapters 14, 15, 16, and 17, 4 chapters here, kind of holistically. A little interesting tidbit. That is how you typically spell holistically, but then I was thinking that doesn't really make sense because holistically should mean whole, as in W-H-O-L-E. I actually looked it up. You actually can now spell it holistically with the W in front. But anyway, that's the more traditional spelling. I want to do these chapters as a whole, which might be a little confusing then as far as how we're going to do homework. So what are we going to do? Today we're going to jump ahead, cover some of the main facts from chapters 16 and 17, the most important facts that will allow us to come back and understand chapter 14 better especially. Because chapter 14 is a little tough. So I think we need some of the content and the examples and the theorems from chapters 16 and 17 to then help us understand chapter 14. So I think hopefully by the end of the lecture, we'll come back to chapter 14 and relate it to the ideas there with examples relevant to that chapter. But then you might wonder, well, what about chapter 15? Friday we'll continue doing this as well as working in chapter 15 as we go. Chapter 15 is about ring of homomorphisms, which of course would be generalizations of group homomorphisms. And there are analog properties, and for example, there's a first isomorphism theorem for rings, just as there was for groups. Okay, so we'll work that in as needed. Next Monday and Wednesday we'll continue filling in details and solidifying details from all of these chapters sort of all at once, thinking of them holistically. No completion problems will be due to be turned in during this time. So no completion on Friday, Monday, Wednesday of next week, and maybe Friday of next week. There will be a few graded problems to turn in. Which I say down there. I will be working on keys still for suggested completion problems to just do as many as you want of those. It's up to you how many you want to do. I would recommend doing as many as you can because this is pretty tough stuff, I think. Chapter 14 especially. And then in chapter 17 it gets a little tougher again. Chapters 15 and 16 I thought don't feel quite as tough, but 14 and 17, the bookends here, kind of feel a little tougher. So, but we're trying to tie it together. Give it some meaning. Give it some organization to help us see connections. That's kind of the main thing. So again, no completion problems to turn in. There'll be suggested completion problems. I'll still give you keys. You'll still probably want to go in the order of the chapters. So before Friday, you'll still probably want to work on chapter 14 completion problems. And the few graded problems that I give you will probably be from, well, at least one from chapter 14 for Friday, maybe also one from chapter 13. I'm not quite sure about that. I have to decide after class here today. Okay? And to make the scores more comparable, instead of 5 points per completion problems, it'll be 10 points, which will make it less likely to get as high of a score as many of you have been getting recently. But work hard and I think you can do fine. Okay. So that's the plan for through next Wednesday, and as far as the homework goes, possibly through next Friday. There's a tiny bit of tidying up that I'd like to do before we jump into chapters. If you look at the lecture plan here, I'd like to do a brief discussion about what are called direct sums of rings before we get into the other stuff. This is going to be real brief. The other stuff involves polynomial rings in general. We talked about particular polynomial rings. Division algorithm for polynomials instead of numbers and its consequences. Irreducibility of polynomials, over a field, which basically means polynomials that are in some sense, you might call them prime polynomials in a sense, as an analog of prime numbers. And ultimately, relationship to maximal ideals from chapter 14. And calculation, an example or two from chapter 14. And again, I will do examples along the way. They'll be relatively simple examples I'll talk about. But at the end, hopefully this example that we get to will be more challenging and more like those examples that were more difficult to read. But yeah, a bit of tidying up first. Let R1, R2 through Rn be rings. In analogy with the idea of a direct product for groups, we can define direct sums for rings. The terminology distinction is a little confusing. The notation is the same, actually. The set of all n tuples of elements from these sets with addition and multiplication done component-wise is a ring called the direct sum of these rings and is denoted by the same symbolism as we use for direct products of groups, or we call this a direct sum of rings. Why do we call one a product and one a sum? I always found that a little confusing. Actually, with group theory, there's an idea of a direct sum as well. And the relationship between direct sums and direct products is a little confusing. There is a distinction when you've got an infinite number of groups in the product or sum, so to speak. There is a distinction, but don't worry about it. It is a different terminology. You've read about this. You actually even had a few problems on this, I think. But I bring this up because it is in the book, and it's a way to construct new examples of rings. And they can be weird, even if the summands aren't. For example, consider this simple example, the direct sum of z with itself. Why is that weird? Well, for one thing, it's got zero divisors, even though z itself doesn't have any zero divisors. Z itself as a ring, that's an integral domain. Not a field, careful. Right? It's an integral domain that doesn't have any zero divisors. It's a commutative ring with unity with no zero divisors. It's not a field. The only, the unity in there is 1. The only units are plus or minus 1. All the other elements are not units. So it's not a field. But once you do this direct sum of z with itself, it is a commutative ring with unity. The unity is 1, 1. But it's no longer an integral domain. This is not an integral domain, and therefore also not a field. It's got zero divisors. For example, 1, 0 times 0, 1 are two non-zero elements that when you multiply component-wise, which is actually kind of a strange operation compared to what we usually do with ordered pairs of vectors. We don't usually multiply them in this way, but if you do the operation component-wise, you get 0, 0, which is the additive identity in the ring. Okay? So, I bring it up, it's in the book. It's a way to construct new examples, and oftentimes those examples are quote-unquote weird. You might even say always that they're weird when you've got more than one term in the summand, or term in the sum here. Okay? All right, on to this holistic approach to chapters 14 through 17 now. So I'm jumping ahead now to chapter 16. Okay? So we've talked about polynomial rings to a certain degree, to a certain extent. The degree is going to have another meaning. We've talked about, well, a fair number of examples, including examples in Zx, where the coefficients are integers, Rx, where the coefficients are real numbers. Did we even consider an example or two where the coefficients were, say, from Z3? Did we consider an example or two like that? I think so. Okay, those are rings of polynomials. you can define more those are examples. You can define more general rings of polynomials. Let R be a commutative ring. The following set of formal symbols, quote unquote, not really being precise about what that means, is called the ring of polynomials over R in the indeterminate X. In set builder notation, it looks like this. R of X is the set of all expressions, is another word you could use. Formal symbols, just things that look like this, where the A's are ring elements from the ring R. Over here, the rings were Z, R, and Z3. We are going to go ahead and assume R is a commutative ring, though you can talk about polynomials over non-commutative rings as well, but it's simpler over commutative rings. Okay? So we're keeping ourselves to the simpler case. N is a positive integer. Here is Z plus. I'm taking to mean positive integer. When you write it like this, at least. Actually, in a sense, N can be 0. The book phrases it as positive integers, I think. When N is 0, you don't have any of these X terms. You only have a constant term. You have a constant polynomial. The A's are the coefficients in front of these X's, to these powers, so to speak. But really, when you think about this as a ring, and I said this before, you want to sort of forget the fact that this can define a function, that you can graph this function, that you can plug numbers in it, at least initially. You want to just think of the X's to these different powers as being placeholders, so to speak. In fact, a better definition of this ring, in a sense, as a set, is a set of ordered infinity tuples where only finitely many things are non-zero, almost like a direct sum. Where you put maybe the constant term first and then the first power of X second, the coefficient of the first power of X, the coefficient of the second power of X next, etc. And then a bunch of zeros. It's an infinity tuple, infinitely many components. Really more of a sequence, in a sense, from calculus. Why a bunch of zeros? Because there are no higher powers of X. Though, for another example, there could be higher powers of X. So you want to allow yourselves to have an arbitrarily high power of X in the expression up here. It's, in a sense, it's better to think of it that way, but even though that's technically better, it's more natural to think of it as you've always thought of it. Think of these as being objects that look like this. Two ring elements in this ring are considered to be equal if and only if their corresponding coefficients are equal. So you got some expression like this and another expression like that with B's, say, instead of A's. N would have to equal Bn, An minus 1 would have to equal Bn minus 1, etc. The highest power of X that you would see, it would have to be the same. All the higher powers, so to speak, would be coefficients of 0. Okay, just like you would guess. Addition and multiplication of these ring elements is done just like you would guess, and I'm not going to define it precisely. The book does. It's especially nasty to try to define it precisely with multiplying two polynomials. If you're interested in looking at it, it's at page 277. They give a formula for the arbitrary kth coefficient of x to the k in the product of two such polynomials. And it's kind of a nasty formula, though if you think about it carefully, it does make sense. Okay? I'm just going to go ahead and not worry about defining that, not worry about proving this as a ring. It's, to tell you the truth, it's kind of boring compared to other stuff we can do, okay? And it's not that enlightening. You're like, well, I already know this. Kind of thing. Okay? But you should certainly be able to multiply two polynomials. For example, let's do another example in Z3x. You could multiply, for example, 2x plus 1 times x squared plus x plus 2. Technically speaking, what I'm showing you is based on this, on the distributive property. That would have to be proved, actually, based on the definition of addition and multiplication of ring elements in this ring. But we're going to just do it like you should know how to do already. For example, well, if we had two binomials we could FOIL, but we got a binomial, 2 terms, and a trinomial there, 3 terms. The way I typically do it is I go to the first term there, multiply times every term here. So I have a 2x times x squared is 2x cubed. Then I have 2x times x is 2x squared, and then I have a 2x times 2 is 4, mod 3 is 1x. Forget about the x. 2 times 2 is 4, but mod 3 is 1. So now the coefficient becomes 1 times x. And then I go to the next term there, the 1, and I multiply that times each thing. And I typically do try to put it underneath, line up like powers. So I have 1 times x squared is x squared, 1 times x is x, 1 times 2 is 2. Then add by adding like terms. Be careful, you only mod by 3 here with the coefficients, not by the powers. So that 3 there does not become 0. 2x cubed plus 2x squared plus x squared is 0. 3x squared is 0. The coefficient would be 0. You don't have to write it. You can write it. You can write 0x squared if you want, but you don't have to. Plus 2x plus 2, I guess I don't need 2 plus signs in there now. If you want to put some space in there like I did, it's fine, you don't have to. That would be, if I've not made any mistakes, that would be the answer. Does that look good to people? Stop me if I make a mistake. Okay, so addition and multiplication done just like you think they should be. Via the coefficients are combined via the operations in R. In this case, R is Z3, so we add and multiply mod 3. Some warnings are definitely in order. It is essential to distinguish a given polynomial from, okay, here we're going to think about them like we often do, from the function determined by that polynomial. Different polynomials could determine the same function. Especially over examples like this, like Z3. The book gives an example. I'll tell you what that example is. F of x equals x and g of x equals x cubed, thought about as being elements of Z3x, are indeed distinct polynomials. Distinct polynomials. But as polynomials that would determine functions, from Z3 to itself, they determine the same function because for any given input, you get the same output. There's only 3 possible inputs. 0, in which case they both give you 0. 1, in which case they both give you 1. And 2, in which case they both give you 2. 2 cubed is 8. Mod 3 is 2. It's a finite domain here. We only need to consider these 3 cases. These 2 distinct polynomials, if you think of them as functions from Z3 to itself, determine the same function. But they are different polynomials. They have different degrees, different highest powers. And as I said a few minutes ago, also make sure to only reduce the coefficients mod n and not the powers if the ring is Zn. Okay? This should not seem too difficult when you think about examples like this. But again, you can talk about polynomial rings where R is non-commutative. You can talk about polynomial rings where the coefficients are matrices. Doesn't that sound wild? But then the theory is harder. We're doing the simplest case. Some definitions, a theorem and its proof. The definitions, I'm not going to say what they are on the board and on the screen, but on the board I will briefly write some things, but not really fully define these in writing. Define the ideas of degree of a polynomial, leading coefficient, monic polynomial, and constant polynomial on the board, and write notation for degree as well. That's just essentially instructions to myself here. When you got a polynomial, say in the general form, written like this, it is, by the way, assumed, as you would probably assume without me telling you, that there are no higher powers of x when I write this. You should also realize that if I'm writing it like this, I am sort of implicitly assuming something. I am implicitly assuming an is non-zero. Because if it were 0, I wouldn't write it. So that's really an implicit assumption. Implicit assumption, in general, when you write something like that, unless you say otherwise. But then if you did say otherwise, why would you even bother writing? And then when an is non-zero and you've got a polynomial written like this, and again it's implicitly assumed that there's no higher powers, you say the degree of this polynomial is that highest power n. And notationally, the notation for the degree is deg f of x. Degree of f of x is n. By the way, another bit of comment about the notation here. When we are talking about the polynomial, it's not that I'll mark it wrong if you do this, but you want to typically avoid just writing the function name, so to speak, just f or just g, for example. You do want to write, even when you're talking in the abstract, you want to write f of x. When you're talking about the function defined by the polynomial, then you can just talk about f. But the polynomial itself is the expression, the output of the function, it's f of x. What's a monic polynomial? Or first, what's a leading coefficient? Well, that coefficient that is implicitly assumed to be non-zero here, by the highest power of x, that is the leading coefficient. And by tradition, when we're writing polynomials this way, we usually do write them from highest power to lowest power. But you could switch it around the other way. You could write from lowest power to highest power, and that's kind of what I was doing with the infinite tuple that I wrote on the board. I was starting with the lowest powered coefficient and going higher powers. In fact, you can theoretically put these different powers of x in any order you want. And that actually even works even if the ring of coefficients is not commutative. Because it's not really, you're not really adding anything here, so to speak, when you're just thinking of it as a symbolic expression. When you think of it as a function, then you do actually add. But when you're thinking of it as a symbolic expression, it's just an expression. It's just symbols that do have some other meaning, but we're not thinking about that other meaning sometimes. By the way, I didn't need to do plural here, leading coefficient. A polynomial is monic if the leading coefficient is the unity 1. F of x is monic if an is 1. We do assume the ring has unity, the coefficient, right? Actually, we didn't assume that. Okay, well, if the ring had unity, then the polynomial would be monic if the coefficient of the highest power is 1. Okay. And pretty much all the examples we do, the rings will have unity. All right, here's a theorem. If D is an integral domain, which of course are rings, D is our ring here of coefficients, then this polynomial ring is also an integral domain. That sounds nice. Before we look at the proof, you might think, well, wait a minute. Didn't we just look at that example with the direct sum? And we had the direct sum of z with itself, and it turned out to not be an integral domain. And didn't Dr. Kinney just say also 5-10 minutes ago that polynomials can be thought of as infinite tuples of things? Wouldn't it not be an integral domain? Careful, the multiplication. If you think of the polynomials as being infinity tuples of ring coefficients, where you have only finitely many that are non-zero, the ring operation is not the same as the ring operation with the direct sum. It's not the same ring operation. It's not component-wise. So that's a distinction to make. That formula for the kth coefficient when you multiply two polynomials is not component-wise multiplication. You're not saying ck is ak times bk. It's more complicated if you look at page 277. Much more complicated. So it's not the same ring. Not the same idea. Here's it's a pretty easy proof here. Here's an outline of the proof. We already know, so to speak, well, I haven't proved it. I'm assuming we know that d of x is definitely a ring, according to these operations. It's quote-unquote easy to see that it's commutative when R is commutative, and it has unity 1 when R has unity 1. Well, and D is an integral domain, so D will be commutative. It will also have a unity. It also has no zero divisors. All that's left to do then is to prove that this ring D of x has no zero divisors. It's left to show it has no zero divisors. But to do this, it's a pretty easy proof. Just consider what happens when what the leading coefficient will be of the product of two non-zero polynomials. Here's an arbitrary non-zero polynomial, say. And here's another one, possibly of different degrees. I'll call the degree m here. When you multiply these, I'm not going to actually do the multiplication out completely, but we can at least multiply the two highest powers of x to get the highest power of the product, which will be degree m plus n. Which reminds me, I forgot to say something about degree. I didn't fully define degree. Come back to that in a second. Multiply those two highest powers, you'll get the highest power of the product. It'll be an bm x to the n plus m. I am implicitly assuming in writing this that an is non-zero and bm is non-zero. And d, these things are in D, an integral domain. Therefore, this product an times bm cannot be zero, because D is an integral domain. And therefore, the polynomial cannot be the zero polynomial. Which brings me back to the definition of the degree. I did not fully define the degree. I said the degree was the highest power of x in the polynomial. Well, what if it's a constant polynomial, for one thing? Should the degree be zero? Yes, it should, except if it's a zero polynomial, the degree is actually undefined. You might scratch your head and wonder why. We'll come to that later. So the degree in general is the highest power of x that you see when you write the expression from a polynomial. If it's a constant polynomial, highest power of x, so to speak, is 0, so you don't typically write x to the 0. If it's a constant polynomial that's not 0, then you say the degree is 0. But the 0 polynomial has undefined degree. Technicality. That is worth remembering. All right. So now we're on to looking at the main meat of today here. The division algorithm and its consequences. Slide 1. There's going to be, I think, 4 slides related to the division algorithm and its consequences. What's the division algorithm? Well, you already know the division algorithm for integers back in chapter 0. Divide two integers, a divided by b, you get a quotient and a remainder, which means you can write a as b times q plus r. And q and r, the quotient and remainder, are unique with respect to the property that r is greater than or equal to 0 and less than b, assuming b is positive here. Divide an arbitrary integer a by a positive integer b, you get q and r, so this is true. Q could be negative. Q will be negative if a is negative. The remainder has to be non-negative, though it could be 0. There's your division algorithm with integers. What's the division algorithm with polynomials? There is one. Let f be a field. So mostly from now on today, the ring is going to be a field. That is the most common kind of polynomial ring to consider, where the coefficients are in a field. The polynomial ring itself here is not a field, even when f itself is a field. Say that again. The coefficient ring here is going to be a field, commutative ring with unity in which every non-zero element is a unit, has a multiplicative inverse. This polynomial ring, though, actually will not be a field. It'll be an integral domain, but not a field. But anyway, we can do division. You got f of x and g of x, polynomials in this polynomial ring with coefficients in a field. There exists unique quotient and remainder, q and r, that are polynomials, such that a similar kind of equation is true. We can write f of x as g of x, what we're dividing f by, times the quotient plus some remainder. And the uniqueness is with respect to a certain property. Either the remainder is the 0 polynomial, or if the remainder is non-zero, the degree of the remainder is less than the degree of what we divided by. The proof is an unpleasant induction on the degree of f of x. I will not do the proof. You can read it. Maybe I've discouraged you from reading it. It's not real pleasant to read through. I think some proofs are pleasant. Doesn't mean they're easy, but they're pleasant. They're enjoyable once you understand them. But I don't know if this one's can be enjoyable even if you understand it. Maybe I'm biased against induction or something, I don't know. Note, it is essential that you be able to use long division of polynomials to find q of x and r of x. And in the special case where q of x is monic and linear, you can also use something called synthetic division. Let's do a long division example and then we'll take the quiz. Say we're dividing x cubed plus 4x squared plus 6x minus 3. I'll go ahead and use the division symbol by x minus 7. Should be able to do long division. I think sometimes these days people don't learn long division, and maybe don't learn long division of polynomials. But here's the way I learned it. I don't know what grade. Maybe 7th or 8th grade, I'm not sure. Put the thing you're dividing into inside, the thing you're dividing by outside over there. That's the lower power over there, by the way. Or possibly equal power. You can divide by a higher power, but that's not typical. I'll tell you what happens with higher power later. You ask yourself, what do you multiply the highest power here by to get this? What do I need to multiply x by to get x cubed? Well, you multiply it by x squared. By the way, I am thinking about this particular ring when I do this. Though z is not a field. I suppose I could be thinking about it this way. That's probably better. Use a field for the coefficients. I gotta multiply x by x squared to get x cubed. Then take that and multiply times each thing here and put the answer below. X squared times x is x cubed. X squared times -7 is -7x squared. Line up like powers vertically. Subtract. These things will cancel as they should. 4 minus -7 is 4 plus 7 is 11x squared. Bring the other things down. We're doing a subtraction from the whole thing. Now ask, what do I multiply this by to get this? See where I was pointing? Or not everybody's looking here. Ask yourself, what do I need to multiply this by? See where I'm pointing? The x to get this, the 11x squared, I need to multiply by 11x. Add that up here. 11x times x is 11x squared. 11x times -7 is -77x. Subtract. 11x squareds cancel. 6 minus -77 is positive 83. One more step. I need to multiply x by 83 to get 83x. Then go ahead and multiply 83 times x is 83x. 83 times -7. What? Negative 581. That's all right. Subtract -3 minus -581 is 578. There's your quotient. There's your q of x. There's your remainder, a constant polynomial. Degree is 0. It's a non-zero constant polynomial. Okay. Talk about the meaning of this more after the quiz.